Hi, it's Mr. Anderson, and this is AP Physics Essentials Video 32. It's on the magnetic field of a wire. Scientists for years and years and years knew there was some link between magnetism and electricity, but they couldn't find it. There were a lot of clues that pointed in that direction. If you take two magnets, let them go, north goes to south, just like positive goes to negative. If you pull them apart, there is a force between the two, and that force gets greater the closer those two magnets get together. It's just like charges. There's an attraction between the two, and actually Coulomb's law applies to both magnetic fields and magnetic forces and electric fields. What they also knew is that magnetic fields are created and can be measured using a compass. So if you take a bar magnet like this and move a compass around it, you can see that it's lining up with that magnetic field. And so what they wondered is maybe if we take a compass and move it next to a charged object, as we move it around that charged object, it's going to point towards the charged object, but it simply didn't. And so it didn't seem like charges were producing any kind of a magnetic field. And then a brilliant Danish scientist named Hans Christian Ørsted moved the charge. And so what he's got here is a current. So we've got a current, or we know now that it's electrons that are moving, but the conventional current's going to be in this direction. And so what he found is that as the current moved through the wire, it actually deflected a compass. So that particle, that charged particle, has to be moving. And so we could demo this in a science lab. Imagine if we have a wire coming out of a table and we just put a bunch of compasses around it. And so we've got the wire coming out of the table. It's coming towards us. And then we've just lined a bunch of compasses up, but we haven't turned on the current. Watch what happens when we turn on the current in that wire. You can see that we're creating a magnetic field around the wire, and we could measure that and where it is. And so if you have a wire that's a straight wire, so not a curved wire, and it has a current flowing through it, then we're going to have a magnetic field that goes around that wire. And we can measure the magnitude of that magnetic field, and it's really based on two things. The first one is going to be the amount of charge, and so how much current we have that's moving through that wire, and there's a direct relationship between the two. The more flow there is, the more magnitude we're going to have in the magnetic field. And then we have the radius, or the distance from the wire. And so again, this wire is in cross-section, and so this would be the radius, or the distance away from that wire. And so there's an inverse relationship from that. The greater the radius is, the smaller that magnetic field is going to be. Now, how do you figure out which way the magnetic field is going to be? Well, the direction is going to be determined by the right-hand rule. And so what you use is your hand again, but the thumb is going to show where the current is moving, and then the curling of your hands like this are going to show you where that magnetic field is. And so in this case, I know the magnetic field is going from the left to the right. I can see that on my diagram right here. And so is the current flowing towards me or away? If I hold my thumb like this, it's coming towards me. So it's coming through the wire at us like that. And so scientists, again, figured out that a magnet is going to generate a magnetic field. And so in this PHET simulation, what I'm doing is moving the compass around the bar magnet. And you can see now the south end of the compass is pointed towards the north end of the bar magnet. But as we move it around to this side, now it's the north end of the compass pointing at the south end. And so if we look at a simple circuit, so what we've got here is a battery and then a wire that loops back. Watch what happens now when we put a compass and just kind of move it around this is just a simple electromagnet. You can see it's not affected by it at all, but once I turn the voltage on, then you can see it's really essentially a magnet. It's a magnetic dipole. And so as we move it around, you can see that compass needle spinning. And so if we turn on the magnetic field, you can see where those field lines are going to be. And I turn the electrons on as well. You can see it's being attracted, or we're creating a magnetic field. Watch what happens if I turn off that current, it goes to zero. You can see that there's no magnetic field anymore. If I move the compass, it's not going to respond. Let's move it in the other direction. You can see now we've got those field lines again. What's going to happen if we add more wires? Well, we're adding more current, and so watch what happens to the electric field. It's getting greater and greater and greater over time. And so here's that right-hand rule. If we've got current moving through a wire, this is conventional current, all you do is just point your thumb in the direction of where that current is moving, and then as your fingers curl around, it's going to show you where that magnetic field is. And so right here, we've got current going up, so I'm going to put my thumb up, and so then we have the magnetic field that's turning around like that. Let's say the current current's going in the other direction, magnetic field is going to go in the opposite direction. How do we quantify it? Here's our equation for that magnetic field. It's going to be the magnetic permeability. Remember, that's the ability of a material to support a magnetic field. And this is just of free space. It's going to be 1, essentially. We then have the current, which is going to be how much electrons or how much conventional current is moving through the wire. Then we've got 2 pi over r. So again, if we increase the radius, we're going to decrease that magnetic field. If we increase the current, so since it's on top of this equation, it's going to increase the magnetic field. Now you might recognize this on the bottom. What is 2 pi r? That's going to be the area of a circle. And that's because as we move farther out from that wire, we're going to have a 2 pi r relationship between the amount of current and then the magnetic field. And so another important thing that you should understand is if we have multiple wires that are going right next to each other. So let's say we have a wire and the current is moving from bottom to top. Can you figure out which way the magnetic fields are going to be? Use your thumb, point it in the direction of the current, so you should have your magnetic fields going like that. But let's say we have another wire right next to it, and it also has current going up. Well, what's going on right here is that we're actually having a magnetic field act on those electrons as they're moving through this wire. And so we can figure out the direction in which that force is going to act. And so we're going to use our other right-hand rule. Remember, that's this right-hand rule where we point in the direction of the movement of the particle. We then have our magnetic field be represented with our middle finger, and then the force is going to be your thumb. So it looks like that. So what we've essentially got is the current in this direction. The magnetic field is going to be in that direction. And so we're going to get a force. So again, we're pointing up like that. I got a magnetic field like that, so the force is actually going to go into the middle of those two wires. And likewise, if we put the other magnetic fields of that wire on, then we're going to get a force that is pushing towards the middle. So if you have two wires and the current's moving in the same direction, there's going to be a force pulling those wires together. And so a way to think about that is if the current flows together, then the wires go together. It's going to pull them together. Likewise, if we are going in the opposite direction, if they flow apart, then those wires are going to be moving apart because we're going to get forces that are moving away from that center. And so did you learn to create a representation of a magnetic field around a wire or a set of wires? Again, always use your thumb, and the more current we have, the greater that field is, and the larger that radius is, the smaller that magnetic field is going to be. I hope that makes sense, and I hope that was helpful.